Hello students, I am Sonali Kelkar from City International School, and today we are going to do the third part of our chapter Gravitation. Okay, and the topics that we are going to cover in this are free fall, to calculate the value of g, then motion of an object under the influence of gravitational force of the earth, mass and weight. I'll just give the introduction of mass and weight in this topic, in this session, okay, that we are going to cover in the next session. So let's start. So let's have a recap first. Now we did in our last session about the Kepler's three laws, right? Now what are the Kepler's three laws? So the first law is the Kepler's law of orbit. So why this is named as Kepler's law of orbit? Because it tells about the shape of an orbit. As we can see here, the orbit is not a spherical shape. What is the shape of an orbit? It is elliptical shape. So the Kepler's first law states that the planet moves around the sun in an elliptical orbit with the sun at one of its focus. Because it is elliptical in shape, the focus is not at the center. There are two foci as we have discussed. Okay. So sun will be at one of its focus and the shape of the orbit is elliptical. Now the second law says that the line that connects a planet to the sun sweeps equal area in equal interval of time, right? Here is the line, okay? There is a line which sweeps a area. Let's take this point is point A and this point is point B, right? And this area covered by this particular line, this area is equals to the area covered over here, right? Now what about the speed? As I've told you that the planet over here is close to the sun, the speed will be more, right? When the speed will be more because the more force is acting over here. And what about the planet when it is over here? You can see the distance of the planet from the sun is more. So the speed over here is less, right? So irrespective of the speed, irrespective of the speed, the area covered by the planet will definitely same in equal interval of time, right? Now coming to the Kepler's law of periods, that is Kepler's third law. It says that the cube of the mean distance of a planet from the sun is directly proportional to the square of its orbital period time t. So let's derive it, though we have already derived the cube of the mean distance. Now the cube of the mean distance is written as r cube. Cube of the mean distance of the planet from the sun is directly proportional. So here we have to use a proportional sign. This is our proportional sign, right? It is proportional to square of its orbital time period. The orbital time period is denoted by t. The square of t is t square, right? Because there is a proportional sign here, we need to remove the proportional sign for mathematical calculation, right? So r cube is equals to, right, here because we are displacing the proportional sign with is equals to sign, we need to introduce one constant here. The constant over here is k, which is a Kepler's constant, right? And this is k into t square. If I want to find out what is k, then k is equals to r cube. K will remain over one side and t will go down. So k is equals to r cube upon t square. Okay. So the derivation of this is not that important. This you will be having in 11th grade, but the statement is very important. With that, you can just write these three steps, right? To the free fall. So today's topic is free fall, very important. As you can see here, what about the ball which is dropping from here? It is directly falling from this hand to the hand which is beneath the other hand. Now you can see these astronauts, right? Skydiver, you can say, not astronauts, skydivers, which are diving high from the sky. They are coming down, and here you can see a person falling from a very heighted building. Okay, over here you can see, can you tell me what are the force applied over here? As we can see, the force which is applied over here is a gravitational pull of the earth, or we can say the force of gravity, right? Here, other than the force of gravity, student, I want you to notice which are the other forces which are acting on these objects. Let's take which is acting on ball, which is acting on the skydivers, and which is acting on this person, right? As you can see, the force, definitely the force which is pulling them down is nothing but the gravitational force of earth, or the gravity, right? It's a gravity. In all the case, the forces is gravity, but we can see that everywhere this is air. There is a medium, right? Air is a medium, right? So because air is present here, so definitely air is also applying a force which is opposite to the force of gravity. This is nothing but the air is applying resistance, right? So we can see there are two forces which is acting over here, right? Like now what is a free fall? What you can make out from these three pictures, from these three moving animated pictures, we can make out that a body, okay, when allowed to fall freely, here the man is just dropping the ball. He is not throwing the ball. It is called dropping. Okay, he drops a ball. Okay, so the man just drops the ball here, right? So the ball is coming down, and the force acting over here, we can say it's a gravity. So when a body is allowed to fall down freely, and the force which is applied on that object is the gravity, right? So this is what is free fall. This is what is a free fall. So when object falls towards the earth under the influence of the earth's gravitational force alone, then these are called free falling objects, and such motion is called free fall. Now let's see the definition. When an object is under the influence of gravitational force of earth only, then we say that body is under the free fall. Is it practically possible? If I tell you that if I fall this feather and if I drop this feather and the coin together from the same height, do you think they are going to fall at the same time? If I drop a feather and a coin, right? A feather and a coin is allowed to drop from the same height at the same time. Do you think that they are going to touch the ground at the same time? In normal condition, no, right? No, in normal condition, no, it is not happening, because there is more resistance given by the feather, because the area of the feather is more as compared to the area of the coin. First, and the second is the weight of the feather, right? Weight of the feather is more. Okay, the weight of the feather is more as compared to the weight of the coin, or we can say the mass of the feather is more as compared to the mass of the coin, right? So that is why under the normal condition, okay, this phenomena is not possible, right? Where both the feather and the coin touches the ground at the same time. That we are going to discuss later. Now let us come to the point over here. Is when a body was falling, you have seen in the last picture, when the body was falling down, when a body is allowed to fall down continuously, the velocity is changing. Velocity is changing continuously, right? Okay, suppose let's take the velocity over here. Let's take it's 2 meter per second square. meter per second, right? And here the velocity is 4 meter per second, right? So every time the velocity is 6 meter per second, every time the velocity is increasing, right? And whenever there is a change in velocity, then we have to say that the body is accelerated. Okay, so definitely when the body is under the free fall, we say that body is accelerated. Accelerated means every time the velocity is changing, and if we calculate, we see that every time the velocity, here you can see the velocity is increasing, and so the acceleration will also increase. Acceleration will also increase because this acceleration is due to, because it is due to the force of gravity, this is due to the gravity of earth, isn't it? Because this is due to the force of gravitational force of earth. So we say that this acceleration can also be named as the acceleration due to gravity, right? And this is A is now represented by small g, right? Children, you should be very careful because small g represents acceleration due to gravity, and the capital G represents, it was a constant, right? Universal gravitational constant. So you should be very careful, and while doing the problems also you should know what is the capital G and what is the small g stands for. Clear? Now let's see more about acceleration due to gravity. Acceleration due to gravity. Now what is the definition of acceleration due to gravity? So whenever the object falls towards the earth, there is an acceleration associated with the movement of an object, right? This acceleration is called acceleration due to gravity, right? Because the acceleration, the change in the velocity when an object is allowed to fall, right? When an object is allowed to fall, then the change in the velocity is also increasing, right? Velocity is increasing. So acceleration is also increasing when the body is falling, okay, down. And closer it is closer to earth, when the body is more closer to earth, the acceleration is more, okay. So this acceleration is denoted by, here we can see the acceleration is denoted by small g because it is acceleration. Definitely the SI unit will be ms minus 2, or we can write m/s square. Okay, and we know that F is equals to ma. Here we are going to derive, okay, we are going to derive acceleration due to gravity. How did we get g? Okay, and then we are going to find out the value of g also, right? So to start with the derivation of g, we should know that the force which is acting on an object is nothing but mass into acceleration according to the Newton's law, right? So this A, because this acceleration, the acceleration which is produced in a free falling body is due to the gravitational pull of the earth. So we say that this acceleration is nothing but acceleration due to gravity, which is represented by small g. Now we will derive this further. Now let's derive it further. Let me take pen here, right? Okay. Now we know that force is equals to mass into acceleration, because we are talking about the acceleration of free falling body. So this acceleration will be replaced by small g, which is nothing but acceleration due to gravity, right? So now let's find out the value of F, that is force, right? Now this force, as we know that this is of gravitational force act between the two objects. Now what are the two objects over here? Now let's consider as object M, an object having a mass small m, and the other object, of course, because we are talking about the gravitation acceleration due to gravity. So the capital M will be the mass of Earth, right? So the first object can be any object having a mass small m, and the second object, of course, it has to be the Earth, and capital M stands for the mass of the Earth, right? As we know that the gravitational force is equals to the product of the mass of the two objects divided by the square of the distance between them and multiply the gravitational constant, right? Universal gravitational constant, we know this. So let's let's substitute these values over here. So F is equals to G, M is the mass of an object, capital M is the mass of an Earth. Now R is the radius of the Earth. Now why we have considered the radius of the Earth? Because we know that the object is on the surface of the Earth. So children, here you should be very careful. When the object is on the surface of the Earth and one of the object is any object on the Earth and the other object is the Earth itself, right? When you are talking about the two objects in which one object is the Earth, right? Then the distance between the object and the Earth will be considered as the radius of the Earth, right? Now this distance is the center of the Earth towards the center of the object, right? So this distance, the capital R, will be considered as the radius of the Earth, right? In case if the objects are two different balls, so definitely the distance from the center of the object, this will be considered as the distance, right? But here, because the object is on the Earth, one of the object can be anything on the Earth and the other is the Earth. Obviously, the distance between the two objects will be considered as the radius of the Earth. This is a very important concept from the point of view of, this is my sign of important, in fact, from the point of view of exam, right? Now, we got the value of F. We know what is F. Now, can I substitute this F in this equation? Okay. So, yes, let me substitute the value of F. So, if I substitute the value of F, right, let me just, here we have just flipped the equation. So, M into G is equals to, we know that F is equals to capital G, capital M, mass of the Earth, multiply the mass of an object divided by square of the distance between them, which is nothing but the radius of the Earth, right? We have to find out the value of G. So I'm going to keep my G on my left hand side and bring this small m on the right hand side, right? And this R square, right? This m will come over here, this m, so this 2 m will get cut, right? So what I'm left with, so I'm left with G, small g is equals to the gravitational constant multiply the mass of the Earth divided by the square of the radius of the Earth. So this is very important. On the basis of this, numericals can be asked. So here we get the formula of G. Or here we have derived the small g, acceleration due to gravity. Now we have to get the value of G also, children. Okay, so before we get the value of the G, let's find out what are the different factors on which the value of G depends, right? So value of G may vary at different parts of the Earth. As you can see, the Earth over here, right? It is not a complete sphere. It is flattened at the two ends, right? It is flattened at the two ends. Let's take this as a North Pole. This is the South Pole, right? If I take the center of the Earth, this, right? And if I see the distance, okay, this distance is smaller as compared to this distance. These are the two ends of the equator. This is my equator, right? This is my equator. And let's see, this is east and this is west, right? And this is nothing but the equator. Clear? Now these are nothing but poles. And if you see the distance at pole, okay, it is much less than the distance of distance of the equator, two ends of the equator from the center. Okay, we are always going to measure the distance of the pole from the center of the earth, and even the distance of the equator from the center of the earth, right? And we know that the small g is mass upon r square, right? If I keep all the other factors constant, I can make out g 1 upon r square. That means it is clearly shows that the gravitation acceleration due to gravity, right, it depends, or it is affected by the distance, square of the distance. If the distance is more, they are inversely proportional. If the distance is more, the gravitational pull is less. If the distance, if r is more, right, if the distance is more, the g is less, the gravitational pull is less, acceleration due to gravity is less. So where you can expect the gravitational pull is less, children? Here, because this distance is more, so on equator the gravitational acceleration due to gravity is less, and on the poles the acceleration due to gravity is more, right? So at poles, okay, at poles small g is more, it is more, right? And at equator the value of small g is little less, right? Let's see what is the value. Over here you can see and at equator it is 9.780 meter per second square, whereas at pole is 9.832 meter per second square. So definitely the weight of an object will approximately 0.5% more at the pole, right? Because the gravitational pull is more at the poles, right? So gravitational pull is more at the pole, definitely the weight of an object is more at the pole, because we still have to do the weight, children. So I'll just do little correction over here. Pole, okay, fine. So we have to do, still have to do weight. Okay, so weight is a quantity which depends upon the gravitational pull of the earth. Simple, right? So because it depends upon the gravitational pull of the earth, because on the pole the gravitational pull is more, so weight will be more here. And how much should be weight, how much is the more weight, additional weight on equator is 0.5%. So 0.5% of a object will weigh 0.5% more on the poles rather than on equator. Okay, so let's go through the statement from here. From the equation G, acceleration due to gravity is equals to gravitational constant, universal gravitational constant into mass of the earth divided by the square of the distance between the object. So children, when I'm talking about small r square, it is this distance between the object. This is the distance, okay, between the object and center of the earth, center of the earth. Okay, and whenever it is capital R square, this capital R stands for radius of earth. Now what is the difference? In the first case, let's take, this is the earth, the object must be somewhere in the on the top of the Eiffel Tower. It's not Eiffel Tower always, on the top of any any heighted building, okay, maybe on the cliff, maybe on the mountain top, right, like that. Okay, and when we are talking about the capital R, then object is of course on the surface of the earth, or let it be little bit more, little heighted place, little heighted, not extremely heighted place, right? over here. Okay, so this case you have to consider the distance as the radius of the earth. In this case you have to add this distance with the radius of the earth. Okay, so this complete distance will be considered as small r. Clear, children? So these are the very important points which you have to keep in your mind while doing problems, numericals. Okay. So this is because the shape of the earth is not perfect. We know that the value of g depends upon the distance of the object from the earth center. Why we are talking so much about the distance? Because we know that the shape of the earth is not a complete sphere. It is just like an orange. It is flattened at two ends, right? That is north and the south, and you can see, right? And it bulged out at the equator. Hence, the value of g is greater at the pole. G is greater at the pole and lesser at the equator. However, for our convenience, we take the constant value of g throughout. Okay, now let's calculate the constant value of g. Now calculate the value of g. We know that the formula, okay, small g, we know the formula, capital G into m. This is the capital G stands for universal gravitational constant, m, capital M, that is mass of the earth, children. While doing the calculation numericals, you will learn the mass of the earth. You don't have to by heart it, and if the question is given, this value will be given to you in the question itself. So mass of the earth is 6 into 10 to the power 24 kg, and the distance d square, the radius of the earth, here they have taken d, that is the radius of the earth. Here it is 6.4 into 10 to the power 6 meter, right? So if you substitute all these value in this formula, you will get g as 9.8 meter per second square. So let's do this. Small g is equals to, right, 6.673, and we can just take 6.67 after the decimal. Make sure that you take 2 digits after the decimal, right, into 10 to the power 11 minus 11, right? And m, the mass of the earth, it is 6 into 10 to the power 24 divided by 6.4 into 10 to the power 6. Make sure that you have to do the square here, right? So this is the point. This is the in this step usually children do mistakes, right? Children do mistakes during this particular step, right? So you can see, as you can see here, this power will get multiplied. You will get 6.67. Let me remove this point, right? This calculation is a little difficult, but you can make it easy. So just first, before you start dividing everything, you have to do 2 steps. First of all, remove the decimals, right? So how to remove this decimal? I can just multiply it by 100, right? I'll just erase it. I will multiply it by 100. So to remove decimal, 667 into 100, right? I'll keep this power same, 6 into 10 to the power 24. We will solve the powers later on. 6.4 into 6.4, so definitely it will be, so 6.4, to remove 6.4 I can multiply here by 10. Again 6.4 I will multiply here also by 10, right? And then 10 to the power, what is 6 into 2? 6 into 2, 12, right? So why we have multiplied 6.4 into 6.4 twice? Because I have to square it, right? And I multiply with 10, so the point got, I can just remove this point from here, right? Here Now you can solve because there is 100 at the numerator and 100 at the denominator, 10 to 10 100, so it will get cut, right children? And here on the top, as you can see, let's solve these no, powers separately. Yes, this is 10. What is minus 11 and plus 24? Minus 11 and plus 24 is 23, right? 13, sorry. 13, right? And this 12, when it will go up, it will become minus 12, isn't it? So what you will get? You will get 10 to the power 1, which is nothing but 10, right? So I will just write over here 10. We have solved all these powers also. So what we are left with? We are left with 667 into 6, right, into 10, this 10, and divided by 64 into 64. Okay, children, when you solve this whole thing, you will get 9.8, or approximately, this is approximate value of this. You will get a 9.77, which is approximately 9.8. This is the value you are going to get at the end. So the value we got over here, the value of acceleration due to gravity is 9.8, and what should be the unit? Meter per second square. For the calculation purpose, it is mentioned in the numericals that you can take 10 meter per second square, but you cannot take it by your own. It has to be mentioned in the numerical. Yes. Now what is this? We know that the acceleration due to gravity, and I have given you one a thought that what about the feather and the coin when I allow to fall, okay, from the top of a building, what will happen, right? So if you see here very carefully, if you see this diagram, there is a feather, there is a paper, and there is a coin which is falling down, and it is touching the floor at a different time. As you can see here, the coin here, yes, it touched first, then paper, and then feather. But what happened here? What is happening in here? Here there is a vacuum, right? There is a vacuum. In this case, there is a vacuum. And what we can see in the vacuum, all are falling at the same time. You see very carefully, all are falling at the same time. Here you can see, right? This experiment was conducted first by Galileo Galilei, okay, and what he told that the acceleration due to gravity, it doesn't depend upon the mass, right? uh, Irrespective of the mass, irrespective of the weight of an object, the object is going to fall at the same time. It is going to touch the ground at the same time, right? This is what we are going to do in this slide, right? The acceleration experienced by an object is independent of its mass. So these two experiments shows that the acceleration experienced by an object, every moment the acceleration experienced by a free falling object is 9.8 meter per second, and it is irrespective of the mass, and the body is going to touch the ground at the same time, right? But this is possible only, as we can see in this experiment, this is possible only when we remove the medium, right? In this experiment, in the experiment 2, the medium over here is air. We remove the air and it is a complete vacuum, and we can see that in a complete vacuum, when the body is experiencing only the gravitation force of the earth, right? Then all the three objects, irrespective of their mass, touch the ground, falls the ground at the same time, falls on the ground at the same time. This experiment way back conducted by the Galileo Galilei, when he threw these two objects from the Pisa, Lenin of when the Galileo Galilei conducted his experiment from Leaning Tower of Pisa. Here is the experiment, yes, which is which is conducted in the recent year. We have this is a whole big chamber, as you can see, and it is complete vacuum. There is a complete vacuum in the chamber, and a ball or a feather is allowed to fall at the same time, and they touch the ground at the same time. So this proves that the acceleration due to gravity, okay, it is not influenced by the mass of objects. Here, now the motion of the object under the influence of the gravitational force of the earth. We have seen that when an object falls towards the earth due to the earth's gravity and no other force is acting upon it, no other force in a sense, the force, the resistance force given by the medium, by air, by water or anything, right? This other force is the resistance force or the force of friction. The object is said to be in a free fall state, right? We know the value of G is 9.8 meter per second square. Okay, free falling objects are not even resisted by the air. G is 9.8 meter per second square, is also called free fall acceleration. The value of G is same on the earth. So the equation of motion for an object with uniform motion are valid where the acceleration A is replaced by the G. Now we can see the differences in the three equation of motions, right? Because when a body is allowed to fall freely, then definitely the acceleration A will be replaced by the small g acceleration due to gravity. Here we can see the three equation of motion. We know that when an object at a rest falls towards earth, when an object is at a rest, its initial velocity is 0. So v is equals to gt. Initially it was v is equals to u plus at, because u is the initial velocity and which is 0. So let me explain you. Initially it's the equation, first equation of motion, v is equals to u plus at. Here children, yeah, so because initial velocity is 0, so u is 0, u is equals to 0, right? So we don't have to write u, but it will become v is equals to, as we know that we are talking about the free falling object, so a will be replaced by g. Okay, A is equals to G. A will be replaced by G. So here you can write V is equals to GT. Clear, students? Right? And in the second equation, we know that second equation here, the second equation, when an object with some initial velocity, okay, here when the object is with some initial velocity, so wherever the small u is used, that has become 0, and the A will become small g, right? So the second equation will be s is equals to t. It should be ut, but u is 0. So t plus half into at square, instead of at square it is gt square. And here we know that 2as is equals to v square minus u square, right? Because u square is already 0, okay, and a is replaced by g, so we can write 2gs is equals to v square. That's it, right? So you can see the different changes in these three equation of motion, right? And when an object with some initial velocity, here the initial velocity is not 0, it has some velocity, then again the whole equation you are going to write same. Okay, you are going to write u because u has value, u is not 0. Only thing over here is a will be replaced by g, right? And when an object is thrown upward, children, this is very important. When an object is thrown upward from the earth, okay, when an object is thrown upward, then the gravity, you are doing some work, you are applying force which is against the gravitational pull. So in this case, the G will have a negative value, right, when an object is thrown upward. Okay, when an object is thrown upward, so G will always have negative value, right? So in this case, you can see this equation has little changes. V is equals to U minus GT, okay, and S is equals to U2 minus half GT square. Because G is negative, so we have put the negative sign in front of half, right? Here minus 2 GS is equals to V square minus U square. Clear, students? So this is all about the equations. So children, let's do question and answers. What do you mean by free fall? We have done this particular topic many a times. Let's repeat this again. The falling of a body from a height towards the earth under gravitational force. There is the only force which is acting on the object is the gravitational force of earth, right? It is called the free fall. Such an object, such a body is called freely falling body. The acceleration of an object falling freely towards the earth does not depend on the mass of an object, right? That means acceleration due to gravity is same on every object, and because of that all objects will fall at the same time. But there are certain conditions on which the object depends, the falling of the object depends, that is the resistance given by the object, okay, given by the object, and then surface area. The resistance is definitely it is proportional to the surface area. More the surface area, more the resistance, right? And that is why you will find the differences in them, okay, differences of the time when they touch the ground in them. During free fall, heavier as well as the light object accelerate at the same time. This we have already done with the help of beautiful examples. Now, at what places on the Earth's surface is the weight of the body maximum? Definitely, it will be at poles, because gravitational Earth depends upon the distance. So G, we know that G is inversely proportional to the square of the distance between them, right? So this the formula itself shows. So definitely if the distance increases, the gravitation acceleration due to gravity is less, and if the distance is more, the acceleration to gravity is more. Children, okay, so the weight will be more. So weight will be more when the acceleration gravity is more, and weight will be less when the acceleration due to gravity is less. Now, what is the magnitude of the gravitational force between the earth and the 1 kg object on its surface? This type of calculation we have already done. We haven't taken the mass of an object as 1. Over here the mass of the object is given 1, but using this formula, and we got the value 9.8 Newton. Because the mass is 1, so there won't be any differences in the calculation, right children? And we have already done this calculation before. So here the force you are getting is 9.8 Newton. Clear? Now, what do you mean by the acceleration due to gravity? So the acceleration of a free fall object, okay, the acceleration of free fall is the acceleration due to gravity, right? The actual acceleration which is caused by the gravity is nothing but the acceleration due to gravity. Simple. We can also say that acceleration of an object due to the gravitational force of the earth acting on it, known as acceleration due to gravity, right? So children, practice today's session, and thank you so much.